Alright, so originally I was going to duplicate every Desmos page I made on my school account to my main one, but then I realized that would take a really long time, so I'm going to do this instead. Alright, so I'm going to cover every single one I made in order that they're listed here. Oh god, there's even more. Oh my god, okay, this is going to be... Okay, well, I'm just going to ignore all of these, like, these ones, because this is just assignments. But then where I start, like, dabbling and stuff is where I'm going to start looking at them. So let's see. That was that one. Blah, blah, blah. Logo assignment. This is what I made. Pretty interesting, actually. I actually turned off the grid and all of that. That was here. Untitled graph, doesn't look like anything. Solving exponential equations, okay. From here, there are two ways to solve it. Yeah, okay. Where was that? That was here. Right. Then we've got parallel strip example. See how that reddish strip that follows the blue line shows all the solutions to the two equations? What am I talking about? Am I talking about, oh, this just purplish strip? Follows the blue line. Well, no crap, that's... Alright. So this is when I was just, like, this is 2020. This is before I even got super sparked into math. This is, like, before the golden era for me. So, like, I'm still, I wouldn't say I was trash at math, but, oh, I remember this. I remember this. I remember this. Yep. I had a whole stage, like a plan of all the different objectives. Yeah, so I wouldn't say I was bad at math. Oh yeah, the cardboard chair. Yeah. It kind of failed. Well, we had to remove some things. We had to remove the armrests, but it worked. I think. Yeah, it did. Alright, summation, understanding. And when there's like multiple versions, I'm just going to choose the one that's most completed. Unless, you know, they look completely different. Yeah, I was in Cadwell's class and I just looked at the board and learned how to do summation from there. Yep, that's how you take a summation. I guess. I don't know. Oops, no, wrong one. Difference between y and f of x. Yep. So y is a relation, which means that it can fail the vertical line test, essentially. F of x cannot. Try including y, right? Well, also just because explicitly here I'm supposed to include y. This is still not really a function. It doesn't pass as a function, because a function cannot fail the vertical line test. But, you know, whatever. Let me see. Untitled graph, logarithms, and exponents. Yeah, they're just inverses of each other is all this is saying. Pretty basic stuff. What do we have here? This looks like an atrocity. Oh yeah, I was infamous at one point for making my extreme graphs. I included like every graph there was on one Desmos thing. What is this? What's the point of, huh? I don't get what this is supposed to be doing, but okay. Man, I am really lost here. Alright, let's... Untitled graph. Has variables that don't do anything. Okay. This is interesting. What is this doing? I'm not certain what this is doing. Oh, this is just 2 points and then solving a linear equation using point slope form. What I don't understand about this though is why did I use the letters F, G, J, and L. Those are so weird. So arbitrary. But whatever. I've got a lot of these functions to go. Alright. Let's go to this one now. Looks like a tangent. Okay, yep, just me understanding how tangents work. Not too bad. Linear equation graph are given 2 points. This is much better. This... Okay. Okay, so I just moved the x1, x2, y1, y2 to solve. So it's in the form ax minus... Okay. Yeah, that's pretty simple. Where a is defined as obviously the slope. H is, I guess, the horizontal offset or something. And K is just the Y offset. I think this is the same thing, yeah. Untitled graph data. 0, infinity. Interesting. Not sure what this is about, but okay. Is this the graph of y equals 1 over x or something? No? 10 over x? Okay. Not sure what the point of that was, but alright. Untitled graph, and this is more for archive, more for preservation than anything else. Looks like I learned how to write exponents as logarithms and vice versa. Pretty soon here we'll get into some interesting stuff. Yeah, this is where I started learning about integral notation. From the lower bound to the... Oh my god, I actually... Okay. Now I would probably say that this is f of x and say y is less than or equal to f of x. Let me try that, actually. I learned this from someone's YouTube video. If you call it f of x instead, it still doesn't... Why is less than or equal to f of x? Maybe, maybe absolute value? I'm not... No. Absolute value of y? No. I'm not certain. But that's where I started messing with integrals. This is where... Oh boy. Oh, yeah. Those are... The sign differences, the only thing here. Yeah, I was supposed to do x2 minus x1. But this is like... I think I was still in Algebra 2 and pre-calculus when I was making these things. So the fact that I was even dabbling in integrals was beyond my understanding at the... Well, not really. Integrals aren't that hard, the basics at least. Derivatives. Yeah, so I guess these obviously aren't derivatives of each other, so I'm not sure what this was supposed to be. Oh, I see. It's taking this and then minus its derivative, minus its second derivative, third order derivative, and so on. I guess that's interesting. They don't really seem to have anything in common from what I can tell. They seem pretty abstract, so it doesn't look like there's a pattern you can derive from this, but whatever. Factorials with addition. This was useful when making my Super Paper Mario thing that I was doing at one point. Yeah, you just use a formula. Deriving the quadratic formula. I'm not even going to go into how this was done. Yeah, because I've got too much here to deal with it. Intriguing thought. Okay, this is where it's going to start to get interesting. This is where my, my passion for math got sparked around the summation or the series notation earlier, but whatever. When x to the a is raised to exponent b, you multiply the exponents. Yeah, yeah. When x to the a is multiplied by x to the b, you add. Yes. doing x to the a plus x to the b, we can find something below addition. That actually is kind of, But yeah, the thing below addition, if you were to go tetration, exponentiation, multiplication, addition, and then tried to go further, it'd probably be the successor function, which is literally just the successor of 1 is 2, successor of 2 is 3, and so on. Successor of 2.1 is probably 3.1 if I had to guess. I don't know. Because addition is iterated successor functions when you think about it. But I don't really know what the successor function is an iteration of. Maybe successors of dx? I don't know. Or d whatever value you're doing, I don't know. Driving discount deception? What? I'm not sure what this is about, but okay. Discount deception. It sounds familiar. Yes, okay. Horizontal stretch and vertical compression. I learned about that at one point. I did not understand the difference, but it has to do with the variable you're affecting. It does. Horizontal compression is different from vertical stretch. Looks like I made a bunch of these. This is interesting. Cosine and arc cosine. Not super interesting because it's not centered at 0, so it's kind of weird. Also, that is... Oh yeah, it is the arc cosine. Tangent and inverse tangent. Oh, ooh, okay, that's cool. Derivatives. What? What is the point of this? Okay, I'm not certain. Pythagorean identities, that's, yeah, pretty simple. Error. I'm not sure. Maybe the differentiation error or something like that. If you take the derivative of negative 1 over x, you get that, and you can't differentiate it at x equals 0. I don't know. I'm not sure if I knew. I think I knew calculus that well by this point, yeah. Because I learned a lot of it at my friend's house at a sleepover once. That's where it really began. Possibly my calculus teacher, calculus AB, thought, had believed that I knew the chain rule already when she was introducing it to the class, but really I didn't. So I kind of played it off. I was like, yeah, guys, I know the chain rule, but I didn't really. I've heard it before, but I definitely knew it was a thing. I just wasn't certain if I knew it, and I didn't. But then I learned it really fast because it's the chain rule. It's not that hard. Yeah, that is the chain rule. Yeah, that looks like it's the chain rule. 3, let's see, times 2, 3. Why is this 2x? Yeah. I mean, if it's, I guess I might have figured it out. I'm not sure. I don't care enough to spend the time to look at it. Derivative of a circle. Yes, this was crazy, because I learned that the tangent was apparently the slope of the circle at a point. So yeah, you can do this with implicit differentiation as well. Miss Cadwell and I worked on this, trying to figure out how to differentiate a circle. Yeah, and it looks like here it is. Yeah, the tangent. The tangent line, that is. Yeah, that looks good. It works. The only problem is that you can't change the tangent slope here. There's no sliders for that, but it works, I guess. Derivatives of square root of x in the unit circle. That is interesting, I guess. I'm not sure I'm not sure why I was comparing them, but whatever. Interesting sum and difference of inverses. So it looks like I'm not certain what I was doing here. It's definitely interesting to look at. I don't know. Derivatives of absolute value. Yeah, so you cannot differentiate. You can't even take the first derivative at 0. Even that is undefined. I don't know what this kind of summation, I don't know what I was trying to do. This is not how summation works. Evidently, I still didn't quite understand summation. I don't know what I was trying to do here. I was trying to sum the set? That... I don't know. I mean... Yeah, I don't know how that would work. And then divide it by infinity. What? I don't know what that is. And I thought that Desmos would recognize ... Or maybe this was just to jot down an idea. I didn't expect Desmos to actually make it work. I don't know. I guess we'll never know. Another quiz. Line partitions. Oh, yeah. Okay, so this is where I started getting into my junior year, I believe, because line partitions, I'm pretty sure, were taught to me in the next math course I did, which was like an online math thing. It was pretty easy overall. It taught me a lot about, it taught me a good amount about like matrices, and a lot of probability, but I forgot that very quickly, if I even understood it in the first place, that is. A lot of times I kind of didn't. But yeah, we got derivatives of midpoint formula. I love independent study on math, but when I'm forced to learn something, it makes me not want to learn it, which is really bad. Asymptotes are inverse roots. Yes, I remember this, and I actually still find it interesting. Maybe it's correct to some degree. So like x minus a, x minus b, you'll have a root here and here, right, at the root factors. Now if you did 1 over that, it would be 1 over x minus a, 1 times x minus b, obviously. But now these roots are inverse roots. They're raised to the -1 power each for them to be in the denominator. Which begs the question, if a root is where the graph intercepts at 0, then is an inverse root, as in a root on the denominator, is it infinitely far from being a 0? Because it's the inverse of a 0. And interestingly enough, it also goes infinitely far from being a root on the x-axis. So that's pretty interesting. I think to some degree it could be true. Obviously, I could be wrong, but I think it's a really interesting way to look at roots and asymptotes. I think it probably could be true to some extent. I mean, it seems too good to not be true. It seems like it just makes too much sense. Measure angles. Oh, I remember this. You had to connect it for some value of c or whatever. Yeah. Yeah, this is the graph I was talking about, but we'll get to that in a moment here. Let's see, we got measure angles. Yeah, that's what I just did. Removable discontinuities exist as roots. I'm not sure what I meant by that. Alright. Why does Desmos break here? Well, let's see. X cubed plus kx, simple cubic equation. We got 6x minus 2. Let's just zoom out here. Okay, we got, so this is the cubic equation. This is the linear. Looks like it's tangent to the cubic equation. X equals 1. We got some kind of weird, wacky curve that's also tangent, I guess, to this tangent line. And it diverges from the value of e. Yeah. So check this out. So this is the definition of e, right? So as I raise this higher, it gets closer and closer to the value of e, right? 2.718281828 and whatever. But then it starts diverging, which is really interesting to me. But it's probably just because Desmos can't handle these kinds of exponents. It's actually, never mind, it's not that interesting. It's just that the calculator breaks for high exponents. Extremely small value glitch. Let's see what we got. Okay. Adding more zeros will make the function glitch out. Let's see. So first, what does it look like? It's pretty much the same. Oh god. Yeah, that's definitely not how the graph is supposed to look. Again, it's interesting, but it's pretty obvious why it happens. R equals, okay, so polar functions. This is the parent function, r equals theta. Then we've got that, which is, whoa, this is pretty advanced for, you know, I understood this at the time I was dabbling in it, and then I immediately forgot it all. That's, wow, that's really interesting. But yeah, I started dabbling in some polar functions. Parametrics are easier. I don't know, I guess I didn't really know about parametric functions at the time. I just saw them on my calculator and I was like, oh, that's kind of scary, and never really looked into them, even though they're easier. This is Cadwell's method. Or no, this is not Cadwell's method. Cadwell's method is where you just look at the highest exponents and the coefficients. This is the formal method, Rivera's method, even though it's both of these are just kind of like they're methods that have existed long before I was taught, but whatever. Limits with, is that this? Yeah. When math does drugs. So yeah, I did this a lot. Although I didn't set them equal to pi, I'm not, no, this is different. Before I would just do every single basic function, y equals x squared, y equals square root of x, y equals e to the x, and so on, and I'd get like this onion shape, since a lot of those functions would connect at the point 1, 1, and have different like exponents. Yeah. But yeah, that's pretty crazy. In fact, let's zoom out. Oh, maybe I shouldn't have done that. Calculus notes. Ooh. Is there a math club? There wasn't, and then I actually made one. The DI method is typically called the tabular. That's correct. Calculus 2, you would, oh, I'm taking Calculus 2 right now. Calculus BC technically, but you deal with these improper integrals. You can deal with them by letting plus or minus infinity equal a variable a and take the limit. That's true. That's the formal way of doing it. What does C do here? It just does that. Can we solve for C if we have the original unintegrated function? If this is possible, which instance? I'm not sure what this is asking, but the video is already 23 minutes, so I don't really want to do that. Oh my god, it's animated? Approximating the sine graph with a quadratic. You know, this is actually the beginning of, I think, a Taylor polynomial. And it is a Taylor polynomial, not a Maclaurin, because it's not necessarily at the point 0, centered around 0, x equals 0. Let me see. Interesting. It's not, I'm not sure. This is, how did I come up with this? How did I derive this? This is so weird, because this does not look like a Taylor polynomial. That's really interesting. I don't know how I managed to do that. I just went gigabrain this day, and then I just crafted that, and then my brain died again. That's really interesting, though. Linear programming, this part was infamous in Algebra 2 for me, because it was so hard to understand what the word problems were asking. But it's not that bad. It's just asking you to optimize by finding the points along the front here, the edge. In multi-objective optimization, it's called like the something front. I forget what it's called, but yeah. Temperature, units, and graphs. So this is where I started learning about the Rankine scale. And I actually knew Kelvin doesn't use degrees. Rankine does, though, which is weird. But yeah. Notice that Fahrenheit equals Celsius at negative 42, is it? No, negative 40. Negative 40 degrees Fahrenheit is negative 40 degrees Celsius. And here, Rankine equals Kelvin at this value. And then they technically don't cross, because all of these endpoints here are absolute 0. That's why it's undefined at this bottom point, is because you cannot reach absolute zero. Well, they're supposed to all be undefined, but I guess it's only this one. Strange. What now? Playing with polar functions. Some more, I see. We've got, yep, that's a circle. Not much to say about that. What is that? Oh my god, what am I doing? How is this not undefined? Let's see, the integral equals 0. It's from negative pi to pi. Does this have an asymptote? It definitely looks like it. Maybe this is an error. You can't... Wait, how is this not undefined? Like, you can't do an asymptote like that and get an area. You just can't. Even if it's an odd function, which it's clearly not, because it's not centered around x equals 0. Or it's not at the origin, I mean. So you can't apply the property here that... I don't understand. Yeah, maybe that is just a Desmos error. Frames per second of the universe, right? So I used like the... Yeah. Oh my god. I think I made this in like an English class or something. I don't know. Oh. Oh god. Okay. Yeah, we're getting... Yeah, I must have used like some... The weakest possible force. Yeah, the Planck units. That was what I was trying to remember. The weakest possible force. Very interesting. That is... Wow. This is like two super small units across the universe of each other or something. That's really funny. Stoichiometry. Oh god. Okay, so this marks the jump. Yeah, you can see June 6th, September 14th. This marks the jump from junior year to senior year. And I'm in senior year right now. Chemistry was torture. Chemistry was torture. And then I started learning about Java, right? I still am. I wrote this to show that Java includes the first but not the last. It includes 0 but not 1. Here this is not centered at 0 is why it doesn't do that, but really it looks like this if you don't change anything. It looks like that. But yeah, cool thing from epsilon delta. Oh god, I don't understand what is going on here. You're supposed to let delta be a really small number. Well, you're supposed to choose epsilon and then solve for delta. I don't understand what's going on in this graph at all whatsoever. So I'm just going to get out of there. Nightmarish decimal multiply. Yeah. Yeah, so I remember making this. It was for programming for Java. So basically, if you select a number like 2330, the expansion is given by this, I guess. 1 point. Yeah, it's gross having to make this formula. I don't know how you would simplify this, because it does have a pattern. It's just, I'm not sure how you would simplify that pattern. But, decimal to binary. It says neater, but it's still, at its root, it's still using recursion, as you can see here. It's based off of previous ones. Okay, this is the top here, so I'm getting there. Focus and directrix generalization. I'm not sure why this is so far out. Oh, I guess it saves from my last one. Alright, so the focus is here. And it changes. Cool. And the directrix is this line here. Okay. My first Olympiad. Yeah, so I actually solved this Olympiad problem without help. I did it in, I think, AP Chemistry in the morning. I was just, like, kind of bored, so I did this. And obviously, you could simplify this work a lot